Okay, Assalamualaikum, my students. I'd like to cover in this short lecture about small disturbance theory. Okay, in other books, some of the book call it perturbation theory. But before we go into the detail, we look at the summary of kinematic and dynamic equations that has been discussed earlier. Okay, the first one, if you look at is the first three equations are the force equation, and that also includes the gravitational effect. The second is the moment equation that also includes there is no gravitational effect, but you have the inertia. Okay, you have the inertia. And then we have another three equations that relate body angular velocities in terms of Euler angles and Euler rates, and the other way around. Okay, three equations that states the Euler rates in terms of Euler angle and body angular velocities. And these velocities, these velocities, dx over dt, dy over dt, this is supposed to be y. And dz over dt, these velocities, this is the matrix of velocities. Okay? This is the matrix of velocity. So velocity aircraft in fixed frame in terms of Euler angles and the body velocity components. Yang ni, this one is fixed frame. This is in body frame. Okay. Now you already have this. Okay? You don't need to derive again, or if you want, you can. But you don't need to remember this. You don't need to hafal okay. But it's really good for you if you understand what each one of these means. Okay. Now, now we consider a small disturbance to the aircraft. Originally, let's say the aircraft is flying at cruising state at fixed angle of attack, fixed pitch angle, zero roll rate, zero pitch rate, zero yaw rate. Everything is in equilibrium. Okay, so it is still stable, equilibrium, statically stable. Okay, and then suddenly there is a perturbation or small disturbance in any of these. Okay, any of these in 3.36. Let's say you have delta U is a small disturbance in the forward speed. The aircraft suddenly, suddenly increases the airspeed, or just slow down a bit, or there is a slight increase in the side velocity. Okay, or there is slight increase in vertical velocity of respect to body. Say there is a wing gust or something like that. Okay, or there is slight roll, slight pitch rate, or a slight. Everything is like a slight increase in X force, a slight increase in Y force, or a slight increase or decrease in Z force and its respective moment. So all these, you have all these delta. Okay, and for convenience, okay, the reference flight condition kita assume sebagai knot, okay, and assumed to be symmetric, and the propulsive force are assumed to remain constant. Okay, so these are all U naught, V naught, this not is a equilibrium condition. Okay, so meaning that the what happened to U is the equilibrium U plus disturbance U. Okay, now back to this assumption. Okay, so based on this assumption, the V naught or the side velocity or equilibrium is zero because you are flying straight forward. Okay, any of the rates, okay, roll, pitch, and yaw rates, they are all zero. So the aircraft is level, okay, and steady, and yes, this phi, okay, roll angle and side angle is also zero. Okay, these are all zeros. And furthermore, if we initially align the x-axis so that it is along the direction of airplane velocity vector, okay, level flight, okay, and airplane, the angle of attack is assumed to be very small, and then and it's not climbing, and then W naught is also 0, so there is no vertical velocity initially. Okay. Now we introduce a small disturbance notation into equation of motion. So let's take the first equation, this one, this equation. Okay. Now let's introduce this. Okay. So we x u equal to x naught plus delta x. So we all add in, and then we neglect all the product of disturbance there, which is basically these are all assumed to be 0. So many things to be 0. Okay, and in the end, the x equation only this one. Okay, only leave us with this equation, meaning that the x naught, which is the original, the initial force plus the disturbance in the force, x force, minus mg sine initial pitch angle, okay, plus the disturbance pitch angle, and that is equal to mass times the change, okay, the change in u, the change in velocity, which is basically the additional acceleration, right? Okay, so and this equation can be reduced further, okay, by the following trigonometric identity. For example, it's a sine theta naught, okay, plus delta theta, and this is equal to sine theta naught cosine delta theta plus cosine theta naught sine delta theta, or equal to this. Okay, it's equal to this. Why? Because we want to make this simple. Okay, make it as simple as possible. Okay, and remember that theta is almost and if all disturbance quantities are set to equal to 0, in this equation we have the flight condition. Let's say this x naught, okay, initial x minus mg sin theta equal to 0. Yeah, so theta is small. Okay, theta naught initially, if it's if you are flying straight and level, theta naught is small. So this should be 0. Okay, this should be 0. Okay, and then what we are left with only is, okay, so y x naught is set equal to 0. Yeah, initially there is no extra x force in equilibrium condition. Okay, so when in equilibrium condition the acceleration is 0, and we're focusing on the disturbance at the additional delta x. When it is equilibrium, everything is 0. Okay, so we have this equation now. Now these are dynamic equations in delta x. So the force delta x is the change in aerodynamic impulsive force in the x direction, and can be expressed by means of Taylor series. So this x itself can be expanded. Okay, so we don't want to know what is the original x naught. No, we don't want to know. What we want to do is to expand this perturbation of x, disturbance of x. Okay, so in terms of perturbation variables, so these are all the variables. Okay, so meaning that the x force, okay, can change because of the change of u, forward speed. That's logical, because the thing is, when you increase the u a little bit, increase the airspeed, you will change the drag. So a drag is in the x direction. And then if you change w, okay, meaning that you increase the angle of attack, you also change the drag. And if you deflect your elevator, okay, a little bit, you get additional trim drag. And if you have additional thrust, it will change your thrust, which is in x direction also. Okay, so delta x over delta u means the change of x force with respect to u, and times delta u, and you get delta x. So we have is the change of x force over the change of w. okay, which is side vertical velocity. Okay, so this one is much more related to drag, and this one is also much more related to drag. Okay, drag maybe because of lift. Okay, this one is also related to the control. Okay, your control surface, and this one is related to the propulsion system. So this delta XO, delta U, delta XO, delta W, and so on is called stability derivative. Okay, and these are evaluated at the reference flight condition. So if you are flying at 100 meter per second, and the delta X over delta U, okay, del X over del U is evaluated at 100 meter per second. Okay, and also the variable delta E or then delta T are the change in elevator angle and throttle setting respectively. So if you don't have elevator but you have kanat, then you just change to C lah, so kanat lah. Okay, whatever you have. If you have elevon instead, you can use elevon. If you have flaperon, okay, because flaperon, okay, it can also increase your lift, your drag. Okay, then put flaperon. If you have all, then put all. Okay, so understand. I hope you understand that. Okay, so these are derivative. Derivative is the change of force or movement respect to the change of velocity or the change of deflection or the change of anything. Okay, so derivative ada unit lah. Jangan kata tak unit, ada unit. Okay, so equation 3.46 shows all this. Okay, dx over du, dx over w, dx over de, and so on, and plus gravitational effect plus equation. That makes one equation. Okay, that makes one equation. Okay, and then you rearrange this equation. Okay, so you know this delta u nanda, this is acceleration actually, so d over dt. Yeah. Okay, so bawa dia pergi sebelah sini, semua bawa pergi sana. Okay, so sebelah sini semua aerodynamics, thrust, forces. Okay, yeah, aerodynamic forces. Control and propulsion to the right. Okay, control and propulsion to the right. Okay, so this actually sebenarnya external factor of the airplane. This is what the pilot do. Pilot kacau kat sini. But this one is sifat semula jadi dia on the left. Okay, ini semula jadi. This is due to aerodynamic. This is due to bumi punya hal. Okay, and then you susun balik, arrange balik. So within that you cancel out all the m, the mass, because you have all the mass here. Okay, you have all the mass. So you divide with the m. Okay, now this derivative, the change ni akan jadi satu derivative khas. So this does not mean ini. Okay, it means this one bahagi dengan mass. Okay, bahagi dengan mass. So this is the change of force. Kali dengan ini, at the end we get force. This is force. You divide by m, what you get is acceleration. Okay, so this derivative, okay, this derivative is basically acceleration per unit angle of elevator or deflection of angle elevator. Okay, so divide by all this by mass. Okay, and you get this, all this. Now this derivative ni yang nak kena calculate. Okay, ini yang nak kena calculate. So in the end of the day you get all this equation. Okay, delta x sekian, delta y sekian, delta z expand sekian, delta l expand macam ni, m expand macam ni dan macam ni. Okay, now I'm going to stop here. Kejap lagi saya sambung balik kat sini. Sebab apa? Lama sangat tadi. Okay, alright. Thank you very much. Tunggu jap. Break.